So what we're going to do today is I'm going to give a bit of an overview of GAMs, and for those of you who are not sort of familiar with those, I'm going to give you a bit of an overview, and then I will take a look at a few of the new features in mgcv and gratia. So given the late start, we might as well just get straight into things. So hopefully you can see these slides. I will put everything up on GitHub, but because of the technical difficulties, I didn't quite get a chance to send this. So before then, okay. Let's start off. If you're not very familiar with these things, let's have a bit of a recap about what GAMs are and how they work. If we have a time series or some data that looks like this, it doesn't have to be time, it could be anything, but we've got some covariate that we're interested in. Here it happens to be time, and we have a response variable that we're trying to model. And if we look at these data, the relationships between the covariate, which is time or the year of the observation here, and the response that we're interested in, there's a clear nonlinear pattern. But it would be quite difficult to think up what kind of model we would fit to this if we were going to stick within the linear model sort of framework. The data that I'm showing here are from the Hadley Center time series dataset. It's the global temperature record, and these are anomalies. So this is the long-term temperature. I think it's the record from the average of the temperatures between 1960 and 1990, but I may have got that dates exactly not quite right. So we're going to have a look at this, and I'm just going to use this as my my example. Now, if we were going to fit this in a kind of generalized or linear model framework, then we would make some assumptions about the data. So here they're temperature anomalies, so we might assume that they may be distributed Gaussian. And then there is each observation is going to have its own mean. And then they're going to share some variance. And because these things are nonlinear, there's no clear pattern here, we can't just put a straight line through them because it's not going to fit the data very well. We might want to try to fit some sort of polynomials where we might have the effect of year plus year squared plus year cubed and so on up to some order j. It might be 10, 15, however many we need to get a reasonable fit to the data. And this model comes with a whole lot of assumptions that essentially that these effects are linear, although that's a bit of a weird assumption when we're dealing with a polynomial. We're assuming that given all these predictor variables, once we've accounted for the pattern in the data, that each of our observations is distributed Gaussian. And because there's no subscript on here, there's no little I in here, this means also that we're assuming that each observation has the same variance. And we're assuming that given the terms in our model, that the observations are independent. Now, the additive model, or GAMs, really don't do anything about assumptions 2 through 4. What they do is they just look at the assumption 1, okay? That we don't have to specify this sort of parametric thing, because here, what order of polynomial should we fit? I think it's quite hard for you to think about a polynomial off the top of your head that would fit those data well. Well, you know, why bother with anything more complex? Well, as I've just said, I think it could be quite difficult to come up with a polynomial that would fit those data well. They're clearly not linear, so we can't just go and put straight lines through here. We do need something that is nonlinear. And if we do try to put polynomials through, here obviously in orange, we've got our linear model, and that doesn't do a very good job of fitting the data at all well. If we add a little bit of wiggliness in here using a cubic polynomial, so year plus year squared plus year cubed in our model, then we're starting to capture the gross feature that there is sort of this increase from the 1970s onwards, but we don't really do a very good job at all of getting close to the data. And it's only when we start to get to much higher orders, like degree 8 or degree 15 polynomials, that we get a reasonable fit to the data. But even with something like that looks pretty reasonable, like here with 8, the light blue color in here, this light purple, we start to see that there are weird features in these fits. At the end here, the curve has, to make sure it's sort of fitting the data in these other places, it's had to do this weird wiggle, and it's suggesting that temperatures were much higher in the past, which would give all the climate denialists something to shout about. And if we go a little bit higher here, so we fit the data even better with this order 15, it's doing something weird very at the end here, but also it's starting to turn the corner and is suggesting that the temperatures have reached a peak and are coming down, which again would be great for the climate denialists. So polynomials are going to be difficult for fitting these things, even though they're pretty good at approximating a particular function. They're not going to be great. They're going to have these weird problems at the ends, especially at the ends of these sequences or of our relationships between covariates and our response. These problems, these oscillations, are related to the Runge phenomenon, and essentially it just means that moving to higher order polynomials won't always improve the accuracy when we're trying to look at their fit to data. And of course, we have a model selection problem here. Do you keep fitting all these different orders of polynomials and then have to choose from among them? And well, then if the computer didn't know, or the software that you're using to do your statistics didn't know about all these other models that you fitted, then you would be our inference would be messed up. And so those p-values and the confidence intervals don't really mean what you think they mean. So GAMs offer us a solution to this particular problem. They offer a nice solution to this particular problem. And you'll be able to follow along with this example if you're pretty quick at typing. Although, actually, I set this up so that it was really easy for you to type in the bits of code, or you could follow along. And then, of course, earlier today, the Hadley Center data just weren't available, and so this was also failing. So I'm just going to move through the example. But we're just loading the data from the internet. There's a whole lot of columns in here that we don't need for this. So we're just going to take the first 2 columns, and then we're setting the names here to be year and temperature. So we've just got our data that I was showing you in the plot. And as I said, as soon as I finish the live stream, I'll get these put up in GitHub, and you'll be able to find them in my GitHub. So the data look like this. We've got our year variable and our temperature variable. And let's just fit a GAM, okay? These models that we want to fit are pretty similar to a linear model or a GLM, if you're familiar with fitting them. The only main difference is that we need to load this extra package, mgcv, which has been written by Simon Wood. So we load mgcv, and then to fit our model, this will look very familiar to you if you've ever fitted a GLM or a linear model. We have a formula here. The function we're going to use is GAM at the moment, but we may use BAM later and things. But we're going to fit our formula. On the left-hand side of the little tilde is the temperature. That's our variable that we're trying to model. That's our response variable. And then on the right-hand side here, this is where you would put the covariates in the model. In this particular case, we just have one covariate, which is year, and I want to indicate to it that we want to have a smooth of year. So we've got S, and we just wrap that covariate in this function S. Okay. We tell it, because we're using a formula, we tell where all the variables are in this formula. So it's in our data frame that we just created a minute ago. I'll talk about why we set method equals REML later. And we should be explicit about our modeling assumptions. So here we're assuming that the data are conditionally Gaussian, i.e. after we've fitted this smooth of year, the observations are going to have a Gaussian distribution, with each one will be distributed Gaussian, basically. Okay, that's the default though, so you don't need to put that in there. So if we do that, we get our model. Here we have the summary of that model. This should look also very familiar to you if you've ever fitted a linear model or a GLM. We get some sort of information about what kind of model was fitted, and then we get information about the parametric coefficients. Now, like any model in R, the convention is that the intercept is included unless you explicitly remove it. So this model, even though we just had a smooth of year, this model includes an intercept, which we have and some information about here. So this is the estimated value of the intercept, its uncertainty, and then some statistics that are not particularly of interest here. And then what is the new thing here is that we also get information about our smooth terms. And they're separated because there isn't just a single estimate, a single value that we can point to for our smooth. So we just get some summary of that smooth, and we also get a statistical test for that smooth. So here is our smooth of year. We see that it's using about 8, a little bit less than 8 degrees of freedom. And the test here is the test for a flat function. So the function is a flat horizontal function everywhere, and it's a test. That's the null hypothesis. And so we're looking for evidence against that null hypothesis. And here we see some clear evidence of nonlinearity and deviation from that flat function. So this is actually, it's pretty easy to fit the GAMs. It's pretty easy to sort of get some familiar statistical output from them. What's more difficult is actually instrumenting the model, getting the model to do what you want, okay? And understanding how it's working are the sort of two main stumbling blocks that I come across with people when they're asking about GAMs. So this is the end result. This is the model that we fitted. And then you might ask, well, how did it know? How did it know to fit that model? Well, we can think of GAMs, and here I've stolen a diagram from Noam Ross, one of my GAM partners in crime. We kind of think of GAMs as lying somewhere between these highly interpretable but not high predictive performance things called linear models, like just a straight line model, and these black box machine learning. I guess this was written before deep learning became all the rage and what have you. But we've got some sort of black box machine learning model here, some big deep neural network or something like that, that has incredible predictive power. It's able to learn features of the data incredibly well, but it's really hard to understand what's going on. So over here, we have models that might not fit the data very well, but it's easy to interpret them. You just read off the coefficients and you know what's going on. Whereas over here, we have these models that are incredibly good at modeling and predicting data, but it's much harder to understand what's going on. And so when Noam talked about this, he essentially put GAMs in the middle. They are quite interpretable. They're not quite as interpretable as a linear model, but we get a graph. We automatically get a function that we can draw for you, so we can understand what the model is encoding. And they are pretty good at predicting because they adapt to the data in the same way that these machine learning tools do. So GAMs kind of lie in the middle here somewhere. So how is a GAM different? Well, we've got some model. So our observations are going to come from some distribution, say, where each observation has its own mean or fitted value on the some fitted value. And then we've got some additional parameters that might get estimated alongside everything. Mu(I) is this expected value of our response, and we model that expected value through some linear predictor. And then here we have a link function. So our linear predictor, that's the thing that we're sort of familiar with. That's where we put the terms from our model. In a linear regression, it would just be a linear combination of these parametric terms where we have some covariate. And as we increase that covariate by 1 unit, we have this beta, its coefficient. It tells us by how much the response will change on the linear predictor scale. And the GAM instead of it being a sum of these parametric terms, it's going to be a sum of smooth functions. The functions, they could just be of a single term, like I'm showing here, but we can have tensor products, so you can have multiple covariates, so you can have two-dimensional, three-dimensional smooths, and so on. But it's now just a sum of these smooth functions. And of course, if we wanted to, we can mix parametric terms with smooth terms in our model. And what interests us is then how does GAM learn these smooth functions from the data? So GAMs do that using penalized splines. And in the animation that I've got on the screen here, I'm illustrating a series of splines. And I'm going to go through a few slides now just describing what this looks like and how these were created. So this is a spline. Some of these curves look smoother than others. They have fewer wiggles. Some of them have got stronger wiggles in them, and so on. Splines are made up of something called they're created from something called a basis expansion. And that polynomial model that we fitted earlier, that was also a basis expansion. It was a polynomial basis expansion of our covariate. So in that model, if you had x raised to the power of 0, then that gives you a constant. So that's that's essentially the covariate that goes with the intercept. X raised to the power of 1 gave us our linear term, and then we had x squared, x cubed, x to the 4, and so on. So x was year, right? That polynomial that we had in there. That is a polynomial basis expansion of x. But we already saw that that was not a good basis expansion, not a good way of modeling the data. Instead, we're going to use splines. And splines are just functions that are made up of simpler functions, just like that polynomial. Those simpler functions we call basis functions. And the set of basis functions, we call that a basis. Right? So we're going to have a spline. It has a basis. That basis contains basis functions. But they're not going to be these typical polynomial things that we've just seen. When we're fitting our model, with splines, each basis function that we have in our basis, so bk is the basis function, it's going to be associated with a coefficient, which essentially scales the basis function. It's like the weight for each basis function. And then the spline that we get out here, our f of x, that is just a weighted sum of those basis functions evaluated at the covariates. So here we have our basis function. It's evaluated at the values of our covariates, and each basis function has its own weight, and we just sum up those weighted basis functions to give us our spline. Well, what does that look like if we draw some pictures? Here we've got a cubic regression spline basis. So here I've got some covariate on the x-axis. I've got some covariate x that we're interested in using to model a response. And I've used, I think there's what, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we've got 10. So there's 10 basis functions here. These are cubic regression spline basis functions. And each one of these little functions has the same shape. They're truncated at the ends because they go off, but the spline really is only defined for the range of the data. But these little basis functions here all have the same shape. You'll notice, though, that they essentially only have some value that is high. They only take on some larger value for a small part of the covariate range. Right? So this sort of light bluey green one in the middle here, it is only going to really affect or have influence on the fitted spline for this part of the covariate, because after that it goes very small. Okay, so we have these little basis functions, and if we choose different kinds of splines, the basis functions will look different, but the idea is going to be the same. There's just little basis functions. So we've got 10 of these things. And then what we are going to do is we're going to give a weight, those betas, we're going to give a weight to each of those basis functions. And those weights just scale the basis functions up and down. So sometimes we've got a large weight. Here, that was a negative weight to the pink one. Now we've got a positive weight, and so on. And then what we do is we just sum up the value of all of these, all of the basis functions for each value of x. So if I want to know what the value of the spline is here at this point, then I just sum up all the values of the basis functions. And depending on the coefficients that we have, the weights for these different basis functions, this is how we get different kinds of splines. Now, I chose these weights here randomly, and I'm varying them randomly just to show how they combine to create the fitted spline. When we're actually doing this with data, we need to put in an extra step. We don't just randomly choose the coefficients. So here I have some data. In the background, we've got this kind of gold curve. That's the truth that I want to try to recover. I'm going to forget that I know that now, and then I've simulated some data from that truth. We're going to forget that we know what the gold line is, and we're going to estimate our model. So when we do this now, so we're going to try and learn the shape of this golden curve that's in the background. That's what we're going to try and learn. The way we do that then is that we want to, rather than choosing the coefficients or the weights for our basis functions in a random manner, we want to obviously choose those basis functions, the weights for the basis functions that make the smooth go as close to the data as possible. Right? So here you see that we're choosing weights that make the black spline that we're essentially fitting to these data. We choose weights for the little colored basis functions. We choose those weights to make the black line go as close to the data as possible. Now, of course, if we had many, many, many basis functions, we could get arbitrarily close to the data. So obviously we're going to need to do something else to stop us overfitting. But essentially, this is the process by which a GAM will work. It's going to choose weights for those basis functions, and that gives us our spline in our model. So model fitting essentially boils down to finding the weights for those spline basis functions that make the spline go as close to the data as possible. But of course, we don't want to overfit, so we're going to need to do something to try to decide. Unlike that polynomial example, we're going to have to do something to decide how wiggly should the fit be. Should it be really wiggly to fit the data really well, or should it be relatively smooth? And so it just sort of gives us a general model, a general for the shape. So we need to essentially choose weights or our coefficients for our smooths, which do two things. They need to balance the fit to the data with the complexity of f, of our function. So we want to have a function that fits the data well, but we don't want it to fit the data too well, because it will become overfitted to those data, and it wouldn't generalize very well to some other data that we haven't seen before. So to do this, we're going to introduce the concept of a penalty. So we're going to have the sort of fit of our model. So the fit of our model here, given the coefficients, is going to be measured by the log likelihood. The log likelihood of the data, how likely is it that we would have seen the data that we observed given these coefficients? And then over here, we've got a penalty. This penalty here is going to be a measure of the wiggliness of that function. And so we've got this trade-off between how well we fit the data and how complicated our function is. Ignore the factor, this 1/2 here. The thing that we've got squished in the middle between the fit of the data and the penalty is this thing lambda, which is the smoothing parameter. It's a hyperparameter or a tuning parameter, but that's the thing that we're going to use in our model to actually choose the right values of betas. And another interesting thing here is that the penalty itself is a function of the weights, the coefficients for our smooths. This matrix in here, S, that's called the penalty matrix. It's just something that gets created automatically when you set up your smooth. Right? But this is the wiggliness of our smooth. This is the fit to the data. And you notice that we're subtracting something from the fit And so that means that this is this is how well we fit the data, but we're subtracting off some element which is due to the wiggliness of our function. So if we made this fit, if we made our model go as close to the data as possible, then it would have to be really wiggly. So we'd be subtracting off from that log likelihood a very large number because our model would be really complicated. And so it would end up with a relatively low penalized log likelihood, which is the thing that we're interested in here. Likewise, if we had a really simple model, then and like a straight line, then the penalty over here would essentially be 0, but we would not get a good fit to data that are not linear. So then that would also give us a low penalized log likelihood. Okay. And then so there's going to be some sweet spot in the middle here where we get a good enough fit to the data, but we're not having too complicated a smooth. The measure of wiggliness is usually, and this is what MGCV does by default, it's usually the squared second derivative of our function summed up over the entire function. So it's the total squared second derivative. So here we've got f and these two little primes. That indicates that it's the second derivative. And then we've got a 2 here, so that's the squared second derivative over x. And then we're integrating that over the range of x. That integral turns out to be computable by our coefficients in some matrix multiplication here, multiplied by this smoothing penalty matrix here, S. So and S is just given to us automatically. So really we have our penalty in terms of our coefficients. And we'll just simplify that to W because that's wiggliness, and that's the right mathy word to use. So we want to penalize wiggliness to avoid overfitting, and that's the key thing here. We don't want to overfit, so we're going to include a penalty against excessive wiggliness. And it's that smoothing parameter, lambda, that defines that trade-off. It's how much price are we paying for the wiggliness. And at some point, there will be some optimal trade-off between fit to the data on the one hand, measured through the log likelihood, and complexity measured by the wiggliness. There'll be some sweet spot that balances the two of those things out. And that's the thing that we're trying to maximize. It's that penalized log likelihood. So if we go back to those Hadley Center data, if we have a very large value of lambda, so that we're paying a very large penalty for having any wiggliness at all, then any deviation, if we made that line just wiggle a little bit, then it would be a massive penalty. And so if we force lambda to be really, really big, so we should have no wiggliness, we get a straight line. Okay, so that's at one end where we've made lambda really, really big. At the other end, if we allow lambda to go really, really small and we're paying very little price for that complexity, then our fitted smooth can get really, really wiggly because we aren't paying a very strong price for that wiggliness. Okay. Well, this one's clearly overfitted to the data. This one's clearly underfitted when lambda's very large. So we need some we need to find some optimal values somewhere in the between. As we allow lambda to go a little bit smaller, then we start to go closer to the data. This looks a bit like that polynomial, that cubic polynomial fit that we saw earlier. And then here is lambda at 0.01. It seems to be doing a pretty reasonable job here, and I can't remember exactly what the final value of lambda is in here, but it is somewhere that's just a little bit more wiggly than this thing here. Okay, so obviously we're going to find this. Now, it would be a bit of a pain if you had to go through and try all of these things, all of these different values of lambda to find something that was optimal. And you'd just be back like you were in the situation of that polynomial where you don't know which order of polynomial to fit. But thankfully, that's what mgcv is doing for us. That's the new kind of thing in GAMs that I think of in the last sort of 20 years has meant that GAMs have become a much more interesting model compared to the original GAM software from Trevor Hastie and Rob Tibshirani, because there essentially you had to tell it how wiggly each of your functions essentially were, and then it would fit the model to give you something like the wiggliness that you wanted for each of the functions. And so I think it was felt that that was a little bit subjective. Now, with automatic smoothness selection in MGCV, we don't need to worry about what the value of lambda is. MGCV will try and find that optimal value for us. So essentially, the modeling with the GAM comes down to you deciding how smooth your functions should be, and then MGCV finding some optimal value of lambda, the smoothness parameter. And there are two main ways that we can really think about how we're going to choose that value, an optimal value of lambda. We could be purely predictive, and so we could choose a value of lambda that would essentially minimize the out-of-sample error. So if we were doing some form of cross-validation, for example, if we left some observations out, fitted our model to the remaining observations and got it to predict for the observations that we leave out, and we would repeat that lots and lots of times, leaving different observations out in turn, and we could find some optimal value of lambda that had the lowest error, some value of lambda that resulted in the lowest cross-validated error. That'd be one way to proceed. But of course, with larger and larger data sets and in practice, it becomes difficult to start leaving out observations. We'd like to actually use all of the data to inform our model. Then we would like to approximate that cross-validated error without actually doing it, so they don't have to fit the model many, many times. And that is why MGCV has its name, because it used this thing called generalized cross-validation. Okay, so that was the original, and it's still the default is to use this generalized cross-validation. But that's this predictive approach where we're trying to minimize the out-of-sample error. An alternative way of thinking about this problem is to be a Bayesian. If we think about this process of smoothing, but from a Bayesian perspective, and put priors on all of our basis coefficients, then we can think of a criterion that then we would minimize that would give us some optimal fit. And when you do that, when you do start to think like a Bayesian and take a Bayesian approach to smoothing, what pops out is a criterion that looks like the restricted or residual maximum likelihood criterion from a mixed model. And so it was realized quite a long time ago that you could actually fit your GAMs in mixed effects software if you just coded everything up appropriately. But that's when you're being Bayesian about it, where you're putting priors on your coefficients. So and we're going to be using sort of improper Gaussian priors on the coefficients. Now, there are lots of different, within each of these two groups, there are lots of different techniques that can be used that allow you to choose the smoothing parameters. MGCV implements all of the ones that I'm showing up here. The one that you mentioned earlier is REML, and it seems to be the thing that tends to behave best in a wide range of situations, and that's why we said method equals REML. And why we suggest that, and why lots of people suggest using REML for doing smoothness selection, is shown in this figure here that comes from one of Simon Wood's papers. It's in the the Proceedings of the Royal Statistical Society, B. And what Simon's showing is that he's got some function over here, and this so software's trying to install something. So we have a function that he simulated some data from, and then estimated a smooth function of those data, trying to fit the smooth function to the data. And then in the middle panel here, we have the values of lots of different values of lambda, the smoothing parameter, and it's shown here as log lambda. but just because, as you saw on this previous thing here, you go to very large numbers to get smooth, very small values to get wiggly. So to avoid that is just showing it in here as log lambda. And then on the y-axis here, there's the log of this GCV criterion. So this is the thing that you would minimize. You want to find the coefficients that would, and the smoothing parameter that would lead to the smallest GCV criterion. I have is the smallest cross-validated error or generalized cross-validated error. And each of the lines in here is the trace of that GCV criterion, or the log of that criterion, for a number of different data sets. So each line represents a different simulated data set from the true function. So the data have been simulated with noise from that true function. And you'll notice what the first thing you should notice here is that there is not a well-defined minimum here. There is not a well-defined minimum for any of these functions. And what tends to happen is that for some of these functions, some of these simulated data sets, you end up having a very small value of the smoothing parameter, and others a much larger value. So you see there's little tick marks on the bottom here. They're indicating the optimal value for each of those. I think it might be 8 different data sets in here. And there's a nice wide range to them. So you could be unlucky and get something that's really wiggly, or you could be unlucky and get something that's really smooth or relatively smooth. And there's a lot of variability just depending on what data you happen to observe. And that's because the shape of this function doesn't really have a nice, well-defined minimum. If we look at the same setup, but where we're looking at the REML criterion, so this is the thing that is I guess it's the negative of the REML, so it's the thing that's minimized when you do methods equals REML. You'll notice that now, as a function of the smoothing parameter, these have a nice well-defined minimum. And they're all clustered for each of these different random data sets that Simon simulated from the true function. The smoothing parameters that are estimated, depending on which version of the data you get, are all nice and tightly clustered around one another. So this is just illustrating that GCV can have a tendency to under smooth. It can sometimes end up at being too wiggly, just because of the data that you happen to observe. Whereas REML, because of the nature of the shape of the criterion, tends to give more consistent, more stable results. So that's why we say REML. You can do ML, so maximum likelihood, or marginal likelihood, I guess, but that's the ML. It works almost as well as REML in the tests that Simon did in this paper. And we'll talk more later about this neighborhood cross-validation, because this is really interesting. But those are the two main ways. If you're being predictive, then you might use AIC or Mallow's CP, or the default generalized cross-validation. If you're being Bayesian about it, then you would use ML or REML, smoothness selection. And then there is this new thing, which we'll look at later. So that we now have a way of representing our splines in terms of these coefficients. We have a way of fitting our model and choosing how wiggly something should be. The next thing that you have to do as a user of GAMs is that you need to choose how many basis functions are you going to use to represent your function. Do you want to use 3 basis functions? Do you want to use 100 basis functions? Essentially, that's up to you. And mgcv will give you a number that it uses, and by default, that's using 10, and we lose 1 for technical reasons. But that's the default. But really, this is the main choice. After you've decided that you want to have a smooth function for a particular covariate, this is the only other thing that you as a user really need to choose, because by default, you should be using method equals REML. So we when we're doing this, we set the basis complexity, or how many basis functions we are going to use to represent our smooth, and our function that we want to approximate. So, and you can think of this value of k as being the maximum expected wiggliness. It's how many small functions would you need to make up the curve that you think is the real relationship? Okay. Now, of course, that's going to be difficult. If you've never fitted a GAM before, if you had a problem deciding how many degrees of polynomial you would use to fit the Hadley center data, you're not going to easily be able to say, oh, well, it should be this number of basis functions either. Okay, so the key thing is that you need to at least have a think about it. If you don't expect it to be particularly wiggly, then you don't need to set k very large. You could set k to be 4 or 5, for example, if you just wanted something very simple. Whereas for some data sets, if we've got a very complicated time series, for example, then you might need to a priori think, well, okay, if it's going to go up and down and up and down and up and down lots and lots of times, then just using the default 10 basis functions is not going to give me a function that will allow that to happen. So that you can already start to think about how large it should be. Okay? But once you've decided on how many basis functions you're going to use, the penalty is going to start to kick in, because MGCV will start off, it could have all that flexibility that all those basis functions allow, but then it's going to start penalizing those things if it needs to. And what you will end up having is, unless you set k to be too low, you will typically end up in a situation where the effective degrees of freedom, i.e. how complicated your smooth is, will be much lower than the value of k that you specified. Right? So usually, this is what usually happens. You'll set k to be some number, maybe use the default, but you'll set k to be some number, and then they'll get shrunk a little bit. Some of the extra wiggliness there is not going to be needed, and so your smooth will end up using fewer than k degrees of freedom. But this is something that must be checked. So the key thing really is that k has to be large enough. The penalty, once you've set the basis up, once you've chosen how many basis functions you want to use, the penalty will usually do the rest, and it will shrink things away. Now, what do we mean by large enough? What we mean by large enough is that the space or the set of functions that could be made up using your basis functions is big enough to include the true function or a close approximation to that true function. So that's what we mean by large enough. It needs to either include the true function, which we don't know, or a close approximation to it. And as you put more and more basis functions into your basis, then the set of functions that could possibly be created by that basis gets larger and larger and larger. So your job is to choose k should be large enough. The main downside to increasing k, because you might just think, oh, I'm just going to set k as large as I can then and let MGCV do all the rest. Well, of course, as you increase k, you increase the computational cost of fitting your model, because each of the basis functions is a column in the model matrix. So if you want to fit a model that has 100 columns in the model matrix, and well, that actually these days on a modern computer wouldn't actually be very large at all. But if you're working with a very large data set, and you might have on the order of tens of thousands of terms of basis functions in a complicated GAM in the model, then of course, if you're setting k to be unnecessarily large just for the sake of it, then you're going to make your model run really slow. So this is one area where you do need to do a little bit of thinking ahead of time. The default often will be okay, except for situations where you're modeling space or time or space-time processes, or where you've got very complex relationships between covariates and the response. If you're doing anything kind of in biology or chemistry and things like that, how does temperature affect the abundance of a particular organism? Well, we might expect that at low temperatures, the organism doesn't like low temperatures, and the organism might not like really high temperatures. There's some sweet spot. So it might have some sort of unimodal curve. That curve is quite simple. We won't expect it to go up and down as a function of temperature. Sometimes we might think the functions that just come right, they start off low and asymptote. Again, those functions are not going to need many basis functions. So you need to think a little bit about and use your domain knowledge to decide whether the function needs to be wiggly or not. And often the default is fine for univariate smooths, but if biologically, for example, you know that the function should be smoother than that or simpler than that, then you can set k even lower to stop it doing perhaps slightly overfitting. Likewise, if you've got a complicated time series or you're trying to model spatial patterns, then k is probably going to need to be a bit larger. Thankfully, there is a function that can help you decide this for afterwards. So you kind of fit the model, and then as part of your model checking, you use this k.check function to determine whether you've got enough basis functions to start off with. Okay, so here we got a little bit of a summary then. So GAMs, they give us a framework that allows us to model flexible nonlinear relationships. They use these little functions that we call basis functions that we combine to make big functions, which are the smooths that were included in our model. We use our penalty, wiggliness penalty, to trade off wiggliness or complexity and generality and the fit to the data. And really, the main thing that you as a user need to determine is that you need to make sure that your smooths can be wiggly enough to approximate this true function that you don't know what the true value is, but you're trying to approximate using your smooth. Okay, but really, why GAMs? I mean, you could do things if you wanted to with the polynomials, or you could use GLNs, but really, why do we want to use GAMs? Well, this is an example that's come from a paper that I was writing recently. A few years ago, I'm essentially working as a statistician now, and the department I work in do a lot of work with production of livestock and what have you. And there's a long history of using statistical models to improve used for breeding, to improve the performance, the production values of animals. And one of the things that people do there is they look at these lactation curves, how much milk or what is the content of the milk throughout a period of time when a cow has given birth and before it is essentially too heavily pregnant again it needs to sort of start focusing on the developing calf. And so there's a period of time where the animal is milked, call it days in milk here. And then we were interested in what is the milk yield, or in this case, what is the fat content of the milk that is produced as we go through the lactation. And so we got some data here. This what I'm showing here is the average daily fat. So this is the kilograms per day in the milkings. So this is the average daily fat of all the milkings for each week. That's what the data represent. So early on in the lactation, we have sort of relatively low amounts of fat. As we move into the lactation over the first sort of 10 or so weeks, we start to see the fat peak. And then because the animal is now pregnant and some of its resources are going into the developing calf, then we see that gradually the fat content declines. And then at the end of the lactation here, this is where the animal would be dried off. It would be no longer milked because it's essentially preparing to, it's giving all of its resources to its calf that will then be born. And then the whole process will start again and that it will start to be milked. And these functions, these lactation curves, they are clearly nonlinear, right? They have interesting features where the people are interested in where is the peak of the fat or the milk yield in a lactation. They want to know, so where is it? How many weeks or days into the lactation does that peak occur? What is the amount of milk What is the amount of fat or protein, for example, in the milk at the peak? They're also interested in the rate of decline here, because this tells us something about the persistency, how good a producer is that cow across a large range of its lactation. So they're also interested in the derivative or the rate of decline in the function. And so there are a large number of models that get fitted to these lactation curves. They're usually parametric. They usually include some sort of random terms as well if you're doing this to a whole herd of data. But if you're just doing this to a single cow like this, then essentially they're fitting a parametric nonlinear model. And one of the common models, this is Wood's model. It was published in 1967 in Nature. Is given here. Just know I'm actually if you know anything about this, I'm actually presenting this slightly differently. This term kappa in here normally goes in as a negative in Wood's model, but because of the link that I'm showing to a generalized linear model, or in here, I've left it as a kappa being positive. So the parameter values I'll get out of this thing exactly the opposite, or the negative of the things you would have got traditionally with Wood's model. But anyway, this is a nonlinear equation. We're modeling the fat as some function of the week, of time. We have our parameters in here, alpha, delta, and kappa. It's a nonlinear model because delta is one of the parameters enters here nonlinearly. It's entering as a power, and so on. And in this case, they're assuming that these observations are distributed Gaussian, so there's some residual term on the end that they have. And actually, the where I got these data from, there's a link is in the slides sources. They were demonstrating that actually, if you linearize this and fit it like a GLM, then this model actually is a GLM. And so you don't need to make the assumption that the observations are essentially Gaussian. You could use something else. Now, they used a gamma. That actually has the wrong mean variance relationship. So here I'm going to use a Tweedy one. Okay. But doesn't really matter what we're using in here. So we're going to model our observations. The fat observations are going to be modeled according to some distribution. Here we're using Tweedy, but it could be log normal, it could be gamma. Each observation is going to have its own mean, and then there's some extra dispersion or power parameter to be estimated here. And then these GLMs, we use a link function. So the Tweedy, the default is to use the log link. So that's what I'm showing here. But actually, that's the one that turns this model into an equivalent of this. It just linearizes this. So we have beta 0. Beta 0 is log of alpha. Beta 1 is the log of delta. And beta 2 is kappa, if I remember rightly in here. And so this is our model. So we include time as we got one term, which is the log of week, and then week goes in, okay? And we're going to estimate these fixed parameters. Now, Wood's model and the GLM version have a fixed functional form, and that we hope that the data follow that fixed functional form. But what if they don't? And usually the data aren't actually that helpful. They're not that kind to us that they do actually follow those fixed mathematical forms. So an alternative would be to, instead of having those two terms for log of week and week that we had in our GLM, we could just say, I want to have a smooth of that time variable. Everything else is the same. We've got our intercept. We have the log, our log link function, and we're doing Tweedy. But now we're just going to estimate that function, that curve, the lactation curve, directly from the data, rather than assuming that it follows this particular model. And we don't need to use Wood's model. We could have plugged in any model that we wanted here. There are hundreds of the damned things that all have different features, but they all suffer the same problems in that they force a particular function to the data, and the data don't usually agree with those functions in some ways. So there's a bit of code in here that's just showing what we're doing. The first one, this is Wood's model, fitted using the NLS function that comes shipped with R. Here we've got the GLM version. Because I'm using the Tweedy, I've actually fitted the GLM version using the GAM function because Tweedy is not an option for the ours GLM function. But there's no smooths in here, so this isn't a GAM. And then here we have our GAM version, so it's just a smooth of weak. To make these two models comparable and to reflect what I was suggesting about using REML smoothness selection, I've put REML for both of these models. But the main thing is not this. You can look at the code, you can study it at your leisure. This is what is the main point I'm trying to make here. So here we've got our data again. This is the weeks in milk on the x-axis. On the y-axis, we have the average daily fat content. And you see both Wood's model in green and the GLM, the Tweedy GLM version in blue. They they get the overall general shape that it increases at the beginning of lactation, rises to a peak, and then declines again. But they overestimate the rate of increase. They suggest that the peak is much earlier than the data would suggest. The peak is much narrower than the data would suggest. And also the way that the decline in the amount of fat in the milk is only right in a couple of places. I mean, it's a bit like a broken watch, right? That's right twice a day. This one's right a couple of times, right? If we contrast that with the GAM fit, well, no, we obviously, I mean, this is what the GAM is designed to do. It gets much closer to the data and therefore gives us a much better understanding of what's going on. Okay. Now, of course, well, we've got our, if we're going to do anything with these models, then if we look at these, if we're going to try to do inference or anything, if we look at the residuals from these models, this is Wood's model. Oh, you can see I didn't really get the title right here, did I? This is Wood's model and the GLM version. They both have a lot of unmodeled structure in them. So the data are conditional upon the terms in the model. These are not independent. We've got struct, which would obviously make our p-values a little bit less reliable and so on. But also, if you're going to take parameters that talk about the decline of this curve or what the value of the peak is, because that's the way you would interpret the parameters from Wood's model, for example, then if these parameters are for a curve that doesn't fit the data very well, then they're not good values to plug into your breeding program. Now, the converse is, well, with the GAM, what do you get? And the one thing I'm actually won't have time to cover today is how we can use something called posterior simulation. So here, this is the peak. Yeah, I want to know where that peak is and what is the value of the fat at the peak. Well, I can do posterior sampling. I can simulate data from my model, from my GAM, and I can estimate where the peak is and put an uncertainty band on it and get an estimate that is workable in the same way as for the GLM and Wood's model. And likewise, I can do the derivatives of this part of the curve over here to look at the persistency and so on. So I can use my GAM that's been fitted to these data and does a much better job of fitting the data. I can use my GAM to get out of the model parameters that are of interest to the breeders, to the producers, just as easily as I can get them out of these other models. But I don't have to force a particular shape to my data. And that, in an essence, is really the key to GAMs. If you do have very good reasons for fitting a parametric model, really good theory, and your data are consistently following that theory, then you don't need to use a GAM. Right? You have a good model there already. Estimate the parameters for that model, and off you go. But where the data then start to deviate from your model, or your theoretical models don't give good fits to the data, then you shouldn't perhaps force those models onto the data and use parameter estimates that are then biased relative to what the data would be telling you, just because that's the theoretical model you have available. And these actually come from a paper. There's a preprint up on Archive where I go through this. And if you want to look at the code then and how you get the posterior simulations for these things, what the peak is and so on, you can go and find the code on the Archive. And I'll put a link in later. Okay. So what's new in MGCV? And this is probably where I'm going to have to, on the fly, do a little bit of fiddling with my streaming software. But what's new in MGCV? So if you are, if you have any questions, you can put them into the GitHub repository that I mentioned in my Blue Sky and LinkedIn posts. If you or you can just post them into the YouTube chat if you want. Then I'll try and keep an eye on the questions, and I'll try and come back to some questions later. If you have posted in the GitHub as a question that you'd like me to look at, then you could feel free to put a note into the chat, and I'll have a look at it in a minute. But otherwise, I'll just sort of move on through the topics that I was going to cover. Okay. So I wanted just to take a look a little bit at what's new in MGCV. And I'm actually, for time reasons, I thought I would have more time. And then when you start actually going through these things, you realize that you're never going to have enough time. We could be here for hours. So I'll probably do some more live streams or videos on this. But Simon Wood has been really busy. There are lots of new families in MGCV, which means that the nice thing about this is that you can then fit a whole data that you can fit models to a whole range of problems using MGCV. And you can, even if you don't have quite the right family that you need, you can really do a pretty good job of working out your model structure first before you have to move on. You might want to move on to something like GLM-MTMB or BRMS, or writing it by hand in Stan, for example. You can do a lot now with MGCV. And in fact, often if you don't need to go the extra complexity from those fully Bayesian things or TMB, then you can work within MGCV for a large range of models now. The two things that I'm actually going to spend a little bit of time on is this, what's new for fitting hierarchical GAMs. And so that we've got this new basis called the SZ, or the constrained factor smooth basis, which is really useful for HGAMs. And then I'm going to do a little bit of explaining about neighborhood cross-validation. There is actually, in the latest version of MGCV, there's this function called SCHASM, which allows you to fit shape constrained models that use any of the families that are inside MGCV. So this is really hot off the presses from Simon at the end of last year, I think it was. But I don't have time to go through today. But this works with any of these families that I'm going to show you now. So these are, I don't know what we got, 2, 4, 6, 8, 10. So there's like 30 maybe families in MGCV, just a little bit less than that now. You've got the usual ones that are like for GLMs, like the Gaussian, binomial, Poisson, gamma, and inverse Gaussian. But we also have a lot of things like negative binomials and Tweedies. This is for beta regression, scale T, and so on, that allow you to fit different kinds of data. So this is for percentage data. This is something that looks a bit like a Gaussian but has fatter tails potentially. Tweedy or negative binomial for count or continuous data, and so on. A multivariate normal and a multinomial model. Ordered categorical, that's quite an interesting family. And then there are a series of families that allow for censoring. So this is a censored normal, a censored logistic, and a censored Poisson. Which families which are really useful. And then there are also these families which we are distributional families. They allow, no, not the Cox PH, but these ones with LSS in them or similar. These allow for you to model not just the mean, but the other parameters of the distribution. So for the Gaussian, for example, the Gaussian distribution is defined by its mean and its standard deviation or variance. Well, you can model both the mean with a set of smooth functions and the variance with some smooth functions or parametrically, you can model both parameters of the distribution. This is for zero inflated, but unlike the name, it's actually not a zero inflated as ecologists would know it. It's a hurdle model, but it's a hurdle Poisson, Tweedy model, extreme values. So there are so many families here now that for most things, you can probably find something reasonable. You can mix the families as well. So this is a generalized family. So you could say, let's say you've got some data that might be presence absent 0, 1 data, which you might normally use a binomial for. And then you've got some count data that are perhaps not over dispersed, so you could use a Poisson. And then you've got some other count data that seem to be over dispersed, and you might want to use a negative binomial. Or you've got some biomass data that Tweedy might work for, and so on. Well, this GFAM allows you to combine that. It allows you to say that these observations 5, 10, and 20 should use a binomial likelihood. Observations 1 through 4 and 18 would use a Poisson. And then whatever, some other observations use a negative binomial and some use a Tweedy, which is quite an interesting way you can combine different kinds of distributions in here. And it's very flexible. Essentially, you can plug in any of these standard ones. As far as I'm aware, it doesn't work for the distributional models. Okay. But for most of the standard families, I think what Simon calls extended families, it works for those. So you've got a lot of families, so you can do a lot of different kinds of data can be fitted without needing to go out to fancier software. Another thing that was really useful in recent versions of mgcv is this SZ basis. And to understand why this is important, we need to discuss HGAMs. So I'm going to spend a little bit of time just explaining what we mean by a hierarchical GAM. So Eric Peterson, Dave Miller, Noam Ross, and myself wrote this paper in 2019, Peterson et al. in Piaget, where we coined this term a HGAM or a hierarchical GAM. And by that term, we talked about this when we were deciding what to call it. But all we really meant by that name, hierarchical GAM, was just to highlight the fact that it was the GAM or the penalized spline equivalent of the hierarchical models that our colleagues were fitting in ecology and other fields. And really, a HGAM is just a GAM that has smooths just at different levels of aggregation in the data. So it's just the smooth equivalent of putting in things like random intercepts and random slopes into the model. You have an overall intercept, and then you might have subject-specific intercepts, or subject-specific effects of some covariate, and a population-level effect of that covariate. Well, in a hierarchical GAM, we can do the same thing, except we don't have to have parametric slopes. We can have smooths instead. And that's all we really meant by this thing, okay? This idea came from this thing called hierarchical models, and it was just a general term that encompasses things like random effects, mixed models. All these terms get used interchangeably, but the key thing with a hierarchical model is that they have effects on the response at different scales, and the data are grouped in some way. And that's really why we were taking the hierarchical from that. That's all we meant. So HGAMs, they're just what we call this marriage of, sorry, my daughter's calling me. I'll talk to her later. She knows I'm live streaming, so I don't know why she's calling me back. So she obviously got something important she wants to tell me. Speak to her in a minute. Okay. So we was just this marriage of hierarchical, the hierarchical GLMs or generalized linear mixed models or hierarchical models and GAMs. So you can call them HGAMs if you want, but they're just really hierarchical models. And actually, they're just a GAM, right? The GAM is such a flexible model that it just incorporates all of these things. And people do like to put names on them. So they'll say, well, is this a GAM with 1 M or a GAM with 2 M's because of the mixed part? Well, really, they're all just a GAM. Okay? But we used this term HGAM because we wanted to highlight the fact that we're putting smooths in at different levels of the hierarchy, just as you would in a mixed model. And we defined 6 models, but you could imagine many more models. The fact that we wrote down, or we talked about these 6 different kinds of models and gave them names like N and G and GS and all the rest of it, is not really, it's inconsequential really. You can fit, there are actually many more models that we would put into this framework, but we talked about these 6. But this HGAMs are not restricted to these 6 models, or 5 functional models, really. Okay. I'm going to ignore this one. So this figure actually comes from this paper by Lawton et al. In ecography, and we're using that, even though we had an equivalent figure in Piaget. It's just that Lawton, the lead author here, arranged this nicely for a slide, whereas we did ours nicely for a paper. So it's not so easy to put it into a set of slides. So I'm stealing it here. Okay. And what we were talking about, or tried to explain in this paper, is that you can think of there as being sort of some, your data might be decomposed into some common pattern, some average or global smooths that tend to affect all of the data, and then some subject specific smooths. Okay. So you have some average term, and then you have smooths for specific groups or subjects that then allow them to do their own thing. So those are the models on one side, but then you might also have some models where there is no global thing. There is no common shape or pattern, right? So models that do have a common pattern, they have a G at the beginning of them, all right? So here, all the observations follow the same form. So in this case, they would just be a single smoother because there is no subject or group variability. If you do have subject or group variability, so these are the lines for an individual subject or data grouped in some way. Maybe this is one location, one site. This is another site, for example. These could be time series. Then you notice that they all sort of share the same pattern on average. They tend to be high, and then they decline, and maybe with an increase at the end. So we could model that as some average, the common pattern, and then some deviations. And or we could model it where there is no common pattern and they have some deviations. So each time series is doing its own thing. Each individual is doing its own thing. There is no common pattern. Okay. But we added in this extra complexity because you could be in a situation like this where you have S, which is shared. They have a shared wiggliness. So all of these gray curves in this figure, they all have the same wiggliness on average, right? Or you could be on these individual wigglinesses where the curves tend to have their own wigglinesses. Some of them are pretty smooth, some of them are really wiggly. So we tried to think of this modeling structure where you include some common or global or average smooth plus your group specific smooths or not? Do you do that? And then for those subject specific smooths, do they share a smoothing parameter, a wiggliness parameter, which is what these ones do in the S style? And if they have their individual smoothing parameters, some are more wiggly than the other, then you had these I's, all right? But of course, there could be more levels in this. There could be, you could have some average term and then some groups. And then within each of those groups, you've got subjects. So you actually have 3 levels, right? So there's no limit to this. It's just that we had to draw a limit under what we describe in the paper to make the paper. I mean, the paper's already long if you go and look at it, but we had to draw the line somewhere. Now, what we called in the paper global effects or global trends, I maybe talk a little bit about an average trend in some of the materials that I've written to talk about it. They're a bit like the population level effects in a mixed model. Importantly, though, I don't think they're necessarily exactly like that because I don't think the world is so kind as to make sure that the smooth for your average one really does work out to be the population one, but not 100% sure about that. One thing I do definitely know is that just as with generalized linear mixed models, when we are fitting with non-identity link functions, then whatever you call that global effect, it is not a population level effect, okay? Because GLMMs and GAMs with these things in here, with non-identity link functions, they're always conditional upon some value of your random effects. They're not a marginal model. So we don't really get population level effects for GLMMs or GAMs, okay? So we tried to call them group level effects and then global level effects, okay, or average effects. But you could, if you want to, you could call them population, but you should put it in quotes because they're not really ever anything. But you have that top level, and then you have maybe some treatment level, and then you've got subjects within treatments and so on. So you see this hierarchy. We're putting smooths in at all of these, potentially all these different levels. So within those, we have these subject-specific effects. They may be smooth, they may be just random slopes, but as if it's a hierarchical GAM, we're probably including smooths. And essentially, these are just repeated observations on the same set of subjects over time, say. They may be nested within treatment groups, and we may or may not have a group level or global effects. So you can think of a combination, a way of decomposing your data into these different levels of effects. And that's really what the hierarchical GAMs are. And really, they're just a way of decomposing this data set that you've got. Do you want to decompose it into some average effect, a treatment effect, and then a subject-specific effect, or do you just want to model the subjects? Or do you want to do away with the average shape and just model the treatments and then the subjects that are in each of those repeated measures for the subjects, for the treatments and so on, okay? So that's the way to think about these hierarchical GAMs. You can plug and play, and you actually have quite a lot of different flexibility in choosing the model, but that also means that you might actually have to fit several candidate models to see which is the right or the best way of decomposing the data. Now, when we looked at originally in the HGAM paper, there were essentially MGCV gave us 3 ways in which we could do this, and one of them isn't really a HGAM-like term anyway. So we had the factor by model. So this is one that we focused on a lot in the in the HGAM paper, and I'll show you an example of that in a minute. We also had this ANOVA-like decomposition. So this is the one that's not really a HGAM because it doesn't give you that group specific, the global or the average term, but it is a way of building in structure. And then we had the random factor smooths. So this is kind of like the smooth equivalent of random slopes. And so there were problems or issues with all of those 3 things. So this is a factor by model. So we have some response is modeled as some parametric factor term. So this is going to give you the different group means. There is some average effect of X. So this is the global or the average effect of that covariate. And then for each of these levels of F, they could be a treatment, they could be a subject. The F is coding for the different subjects or the different treatments. Then we have this bifactor term in here. So this means that we get a smooth for each level of our factor F, okay? So this is the average shape. So this is the black lines from the diagram. So this is the dotted black line that we have in here, the black line. And then the gray curves, these are the other ones. In fact, it's actually more like this one over here because they have their own wigglinesses. So that's great, but we have a bit of a problem here because this function and these functions may look very similar to one another, and essentially they can become unidentifiable. The model cannot tell whether it should be fitting this or this, right? And what happens then sometimes is that it will get very confused and you'll end up having really large credible intervals on your component smooths. where things then don't look statistically interesting as significant. So that was a problem, right? And we fixed that in the paper by specifying m equals 1. So rather than having that wiggliness penalty on these subject-specific smooths, rather than having the wiggliness penalty be on the second derivative, its curvature, we had the penalty on the first derivative, right? Which is fine. And now these two things are getting penalized in a different way. And in the way it works out is that these are all being penalized down to a flat function. That flat function then just measures deviations from this function, right? So it worked out really nicely when we did this. But the problem is that you can only use this with certain types of spline. The trick can only work with the thin plate spline and the B splines, I think, in mgcv. And also, in some situations, it induced a piecewise linear behavior. So the fitted function that you would see would be piecewise linear and have these really sort of bouncy, spiky credible intervals. So they weren't really smooth anymore, right? Kind of defeated the object for what we were trying to do, I guess. But they worked, right? But they weren't ideal, okay? The other way of specifying our HGAMs was to use the ordered factor, but as I said, this ordered factor is not really a true one. We have our ordered factor in here. We have this smooth. This smooth now represents the reference level, so the first level of your factor, okay? And then these are smooth differences between the reference level smooth and each of the other smooths, other levels, so the smooths for the other ones. So these are smooth differences. This is not the average smooth. This is the smooth for one of your treatments or one of your subjects. And these are the smooth differences for each of your other subjects or your other treatments. Okay. And so this works okay, but you have to be really clever about which level you choose for your reference level. Because if you don't get this right and don't choose this carefully, then these ones can be really complicated or not easily estimated from the data. And so everything might get forced to look like this. Okay. It's actually a bit of a problem here in these models as well. Sometimes everything can be forced to look like that as well, right? The global term, all right? Another way of doing it would be to do the average smooth like we did before, but now we use the random factor smooth. So this is a bit more like the random slopes. And it's specified a little bit differently, but you just change the basis here. And this works, and it's fully penalized. So there's nothing that's not penalized. So all of this stuff could be shrunk out of the model if you wanted to. So it is identifiable. But a problem with this is that one problem is that all of these smooths in here share a single wiggliness parameter. So they all have roughly the same wiggliness, which isn't right for some data sets. And also these are a bit more philosophically like a random slope. And usually we choose those things for random subjects, but not for treatment effects. So there's a philosophical issue there as well. To be honest, you could just use this and just do it, but some treatments might be more wiggly than others. So there's a bit of a problem here. The SZ basis essentially allows us to have the best bits of the factor bi model without any of the downsides of having to use that first order derivative. So what we do here is slightly different again, but we have our global or our average term. So this is the black lines. Let's just skip back a few slides. So this is the dotted black lines in here. So we have some global term, okay? But then each of these is set up in a way so that these smooths are made to be orthogonal to or uncorrelated with this, right? So there's no identifiability issue anymore. And we don't have to change the order of the penalty. So these use a second order derivative, like I talked about, the second derivative wiggliness penalty. This uses the second order wiggliness penalty, and so on. So we don't have that piecewise linear problem popping up. We don't have the unidentifiability issue popping up. Each of the smooths, we get one smooth for each of our levels of our factor. And each of those smooths can use a different wiggliness penalty. So some can be really smooth, some can be wiggly. So we have all of the advantages here that we wanted with the factor by model, but for reasons that we couldn't do that in the original HGAM paper. So this is the new thing. And the nice thing about these is that they are pretty flexible. They do allow you to build up your orders of interactions. So this is just the smooth of x. This is the first order interaction between a smooth of x for each level of this factor. And we can start adding up. Here we have a model with two factors. So we have our average smooth. These are our smooths for each level of factor 1, the smooths of x for each level of factor 2. And then here we have the smooth of x for all the combinations of f1 and f2. So this is now the interactions. So it's how does the smooth for different combinations of factors, how does that relationship change relative to these things averaged over f2 or f1? The only thing that you need to note really with this is that you can't do tensor products. These are just for a single continuous covariate. Okay. In the HGAM paper, we talked a lot about tensor product versions of these, but this SZ basis is not that helpful at the moment for tensor products. Okay, so this is, let's have a look at an example now. We'll do something example with some chick weight data, and this is where I'm going to have to fiddle slightly with my software. So if you want to just take a minute to grab water or something, then I will fiddle with my software and get my R up and running in here. Okay, so you're going to see me fiddling with everything. Okay, so we'll just capture my whole screen. That will be easier. Okay. We'll make this a little bit bigger, and I will move this out of the way so we don't need to see that. And I'll shrink the plots out of the way. Okay. Get rid of that as well. Okay, so this is just going to show you some of the features of those SZs in a little bit more detail. And as I said, all of this will be available on GitHub shortly. So we have a series of packages, and we're going to load some data on these chicks, clean them up, because for various reasons, these data are entered. Some of the variables start with a capital letter, some don't. So we just want to get them into a format that is easy to work with. So I've used Janitor for that. So you'll have to let me know in the chat if everything's clear enough for you on the stream. So here we've got our variables. We've got the weight of these different chicks measured at different times. There are a series of different chicks, and those chicks were fed different diets. So if we were to just start off with a factor by model where our response is the weight, there's going to be some effect of diet. But if we don't expect each of the growth curves for the different diets to look the same, have different shapes, then we could just do this and not fit the hierarchical model. We could just fit the smooths for the, yep, I can increase the text size a bit. Hopefully that's a bit better. So they we're just going to fit each, the average of growth rate for each diet separately. That's what this model is saying. So this is not a factor by model in the hierarchical sense. Okay, awesome, perfect. Right, so let's just fit that. And we can have a quick look at what that model looks like. So we can use gratia. So if we do draw that model, then this is what we get here. This is for this is the growth rate for diet 1, diet 2, diet 3, and diet 4. And these are partial effects. They're shown on the scale of the link function. We are model fitting using a Tweedy, so that has a log link function. So these curves are on the they're on the scale of the data, on a log scale. That's why they don't look particularly curved. Okay. Now you'll notice that all of these curves have roughly the same shape. So rather than use certain numbers of degrees of freedom to model the same shape, but do that 4 different times, it might be better to use that hierarchical model where we model the general shape of the growth rate, and then so we model the general shape, and then we model the deviations between them. Right? So if we just look at summary of that model, then let me just make this a little smaller now. Oop, there we go. So you'll see they are all using roughly the same number of degrees of freedom. The plot suggests that they have roughly the same shape. So we, rather than use those same degrees of freedom over and over again, we could model that shape once and then look at the differences. So this is our next model, where, well, I guess we can just tweak this. What we could have done is to have done this. We could have done S of diet by equals, sorry, not S of diet, S of time. Sorry, we don't need that. It's not S. We already have that. What am I doing? There we go. S of time plus S of time by diet, right? That would be a hierarchical GAM, because now you've got this average effect and then you've got these smooth differences. And I'll just call that by 2. So let's just run that. And let's go and have a look at the draw again. Okay. So now we get the global or average effect. So this is modeling that shape. Okay, but now you start to get then we have these other terms in here. They may or may not be suffering from some issues. These smooths don't really look like that one, so maybe they're identifiable enough. But what we would have to do in many situations is put this m equals 1 in there. So let me just do that, because that changes the order of the penalty, and I can show you the problem, one of the problems that we had. These things become piecewise linear, and it's hard to see. Let's see, can I just open? No, that's not the one. I want this. I can make this a little bit bigger. If you notice, this has become sort of piecewise linear, and it has this scalloped nature to the credible interval. That's the piecewise linear nature of it. So this smooth here is no longer linear. It doesn't have continuous and smooth derivatives up to order 2, right? And when they add together, these things can then look as though they're not particularly smooth, right? Which some might consider as a bit of a problem. They don't look too different, so perhaps it isn't causing too much of a problem for this model, but there are clear differences depending on what you penalize. Okay, so let me close that. All right. So ideally, we don't want to have to do that. So what we can do is model the average effect of time, and then have a smooth difference for each of those diets using the constrained factor smooth. So let's run that. And let's have a look at what that looks like in our model. So we're just going to take that model and pass it to the draw function. And this looks like this. Oh, wrong button. Okay, I'll just zoom in a bit. So what we have here, this is the sort of average growth curve for the different chicks. And then on here, what we've got is the how the different diets vary from that. So you can see that some of them, like this diet 4 here, in the yellow, that one grows at a faster rate. So the chicks are growing faster because it's higher, but it sort of then levels off at a little bit higher than this. Whereas diet 1, it tends to grow at a slower rate. So the diet 1's curve would be under this curve and then diet 2 is pretty similar. So diet 2 looks the most similar to this. And then diet 3 is going to be essentially the same shape, but growing much faster. All right. Now, I know how to interpret these things because I've studied them a little bit, for a while. But the real effects are all messed up because you can't sort of see what is the smooth for diet 1 because it's a combination of these two things. So that's something that we'll fix in a minute. Now, what we haven't done yet is we haven't fitted a model that also accounts for the fact that there are chicks in here, and those chicks have been measured repeatedly over time. So this turns it now into definitely a much more complicated hierarchical model, because now we're modeling each chick, we have treatment effects, and then we have average effects of time, all right? So let's run that model. It'll take a few seconds. These ones are random factor smooths, and these ones are the constrained factor smooths. They're going to model essentially the same thing, and then the chick related smooths are going to, okay. Now, this is, I'm running this on a Mac Mini, and I only have mgcv using one CPU core, which is a bit wasteful. So that's why these models are taking a little bit of time to fit. But let's go and have a look at that model. Okay, so I said these things are really just decompositions. All right? We've taken our data and we've decomposed it into some general tendency for the chicks to grow over time. The different treatments, they're going to grow at different rates because all the chicks on diet 1 on average are going to grow a little bit more slowly compared to this overall average thing. Diets 4 and diets 3, they're going to grow a little bit faster, and diet 2, they're going to grow at essentially this rate. But then we also have the fact that each chick, some chicks grow faster than others, some chicks will grow a bit and then level off, some chicks will not grow initially at the beginning, but then speed up, and so on. So we've decomposed the data. We could have just come along and modeled this. We could have just done it for all of the chicks, right? But that wouldn't help us understand something about the diet. And it also wouldn't have, so this is how do the diets, we literally can read off from the model on the link scale, how do the diets differ from one another, right? So by using this hierarchical model, we learn quite a lot about what's going on, okay? But as I said, it's much harder to understand what the growth curves are for the different diets. And that's where one of the new features in Gratia comes in, which is this conditional values function. What you do is you pass it the values you want to condition on. So we're going to condition on time. So time's going to be on the x-axis. We're going to condition on diet. So that will then group the curves by different diets. And then we want to remove or not include the effects of the chicks. So we're setting these so that we're looking at now for the average chick that has 0 random effect. And we do that using the exclude argument. All right? So that's conditional values. And if we pass that to its draw method, we will get a plot. And I keep clicking on the wrong button. This is what they look like. So now we can look and say, okay, now we can clearly see that diet 3 had the fastest sort of growth rates in the latter part. Earlier on, diet 4, they grew faster, but then on average, they didn't grow as fast later on, whereas diet 3, they kept up that growth rate. Diet 2 was intermediate, and then we can clearly see that diet 1 had the lowest growth rates. So what we're doing here is that we're getting predictions from our model that include multiple terms. Does this work? No. No. We're getting predictions that include multiple terms. So we're getting a prediction that includes this and this, plus the intercept, whilst we're ignoring this bit, right? So we can focus on, and you can also focus on a particular chick if you wanted to, and so on with it. Right? And this works very similar to marginal effects and its plot predictions function. So I'll just show you, although we have different defaults, it produces the same plots, slightly different colors, but they work the same way. Okay. So those are our hierarchical models. And I've just shown you there how the SZ basis works. Right, so a question in chat from Andrew. Andrew's asking, why am I choosing SZ here and FS? So really, it's a bit like that. Why do you have a population level slope and a, let me just move to my base cam. Essentially, it means why do we have a random slopes for some of our covariates and a parametric effect? Because we're interested in the diet effects. I'm not interested in the fact that this particular chick versus that particular chick. So this here, I would expect the chicks to have similar wigglinesses. I wouldn't expect that this chick over here, his weight is going to be going up and down, and this one's going to be going all over the place. So what I'm saying, I'm trying to do here is the equivalent of having a random slope for time for each chick, but I'm having a fixed effect of diet, to use that terminology. These are things I am interested in. These are the things I want to do inference on. I don't care that I had access to these chicks and not another brood of chicks when we did this. So that's the reason why we're doing this. Okay. So let me go back to my main thing and then go back to my slides. So that's the SZ basis. I want to spend a few minutes doing this on neighborhood cross-validation. Because it's actually really useful. If you work with time, and hopefully this will work easily enough with space and other things, but if you work with time series, for example, and you want to smooth them, then this is really useful. So I mentioned before that there are lots of different ways of choosing the smoothness parameters, and one of them was this generalized cross-validation. But those things are just there. They essentially assume that the data are independent. The observations are independent. What Simon has done, and you can assume that they're independent if you want with NCV, but Simon has also laid it so that you can do things like H-block cross-validation or step ahead kind of prediction type cross-validation with but you're doing it not to choose the model parameters, you're doing it to choose the smoothness parameters. Okay, you're doing it to decide how wiggly your curves are. And so if you've ever tried to fit a time series with a GAM and you fit it and then you look at k.check and it will say, no, increase k. And you keep doing that and doing it and it's never satisfied. All right. And that's because the REML or GCV don't know anything about the fact that your data are not independent. So now the user interface, like a lot of things that Simon does, the user interface is not the most user-friendly, but it's encoded incredibly efficiently. So doing this kind of weird cross-validation will work even with really big models, i.e. that are really slow, and you can actually do this cross-validation based approach to selecting the smoothness parameters. So it is useful. Right now, I think the easiest way to work with it is to use it for single time series, but we're working through how to do the tooling to make it easier for you to specify these things for more complicated settings like multiple time series in a model like the ones with the chicks we just looked at, or space. All right. And there's Dave Miller has got a really good post up to explain a little bit about that. And so there's a link here to today's post on his blog. Oops. Well, that shouldn't be example chick weights. That should be example NCV. So let's go and see what NCV does. Okay. So let's come back in here. Let's do my weird thing. Let's go back to positron. And let's look at NCV. And I'll explain a little bit more what it's doing now as we go along. Okay. So some packages. And I'm just going to simulate some data. So we have a true function here, and then I'm going to contaminate that function with some AR1 noise. Right. And so I know what the truth of my function is, but I'm contaminating it with autocorrelated noise. So let's just have a look at that. So this is what we're playing with. This is some true function that I want to recover, but the data that I've observed has some autocorrelated noise on top of it. And we'll see in a minute the problems that you can get into when you do smoothing and why NCV works really well. So if we don't know what the K should be, we forget and we set K too large, here 20, okay, or using REML or mgcv, what happens? Okay, well, let's get the fitted values from both of those models and let's plot them. And you'll notice that when we do that, we end up with very wiggly fits. So the red is the REML, so the red is the smoother curve in here, and then the very wiggly one is GCV. So GCV is predictive, so it's trying to predict the data, and it doesn't know that these data are independent, so it tries to fit this wiggly curve. Right? And you can clearly see that we haven't recovered the underlying function properly. We've overfitted because the model doesn't understand anything about the fact that these observations are autocorrelated. So let's now do the neighborhood cross-validation version. And this is what I mean about it being a little bit trickier to set up. We have to specify a neighborhood structure, okay? So we'll set the list for that as a list to contain all of that. And we actually have to specify a couple of things here. We actually have to specify the folds. And actually, it might be easier if I just run this code because it's actually impenetrable to understand. But if we use this function from Dave Miller's mgcv utils package, we can hopefully understand it a little bit better. Okay. So we have to specify we can specify up to two things. We can specify what data should be left out of the model when we're choosing, when we're trying to choose our smoothness parameters. So the model is fitted using all of the data, but when we're deciding how to change the smoothness parameters, we can leave some of the data out and then predict for some observations, right? So the first fold here, what I did was that we were going to go ahead 5 time steps and back 5 time steps from each observation. So this is my first fold here, and it's obviously there aren't 5 observations before, but we've got 5 observations ahead, all right? So I'm going to leave, given my data point here is the first data point, I'm going to leave out the 5 observations that come after that data point. I'm going to leave those out, and I'm going to use those same data points as my prediction set. So I'm not going to use them when I'm choosing my smoothness parameter for this first observation. I'm not going to use these ones we've left out, but I am going to use them when we predict. Right? So this way we say we can leave out some information. Now, as we get here to fold 50, we're leaving out the 5 data points behind the current observation, 5 observations in front of the current observation. So we're leaving out a little window around each observation. And so we're not using the data in this window to fit these data points. All right. But we're only doing that when we're choosing the smoothness parameters. When it comes to choosing the coefficients, because we iterate between these two processes, when we're fitting the coefficients, we use all the data, but they're given this smoothness parameter. So given a value for the smoothness parameter, we estimate the coefficients, then we update the smoothing parameters. And what's happening is that Simon has developed a method that allows you to very quickly do this kind of k-fold cross-validation, for want of a better word. H-block, I guess, is a better word for this, where when you're just focusing on how do we change the estimates of our smoothness parameters, you leave out some of the data around your target point, okay? And we have 1 fold per data point here. My assumption is that you can make more of them or more complicated ones in other settings. So that's the neighborhood. It's a bit complicated, but you have to specify the start and end points of the neighbors, and then the values that are essentially which ones should be in there, all right? Which ones should be omitted and which ones should be left out. And you'll have to read the help and Dave's blog post, I think, given the time. But this is really useful. So let's fit the model really quick, right? Fits the model. Let's now get the fitted values out of here and look and see what it's done. The model we've fitted is exactly the same as the model we fitted before, except now I'm telling it when it's choosing smoothness parameters, leave some observations out when you predict for this data point and so on, right? Let's have a look at the fit. Okay, this is the fit. And you'll see that the fit here is pretty good. It's pretty close to the true model that we saw. So the autocorrelation in these data hasn't upset our ability to recover the underlying function. And if you were to go and use some of the other functions that allow for autocorrelated data, they actually would end up with getting, when you say, okay, these data are AR1 or something like that using BAM or GAM, they also would recover something like this pink line. Okay. So the neighborhood cross-validation is a way of fitting any kind of GAM without having to also specify some autocorrelation function, which actually also has its own problems when fitting GAMs. Okay. Right, now that was I'll just put the two together in here. That obviously is artificial data. Let's have a look at that Hadley Center data. So we're back with our Hadley Center one that we saw at the beginning. I'll answer that question in a second. We're going to do something very similar. In fact, it's the same code. I'm going to do the same idea with the neighborhoods, just for illustration. Okay, we're going to fit our model. This is now using REML. And if we look at this, it's used 10 degrees of freedom. And if we now run k.check here, now that k.check is a random process. So if we set a seed, we'll get the same result each time. So here I've set the seed, and you'll notice it's saying, okay, even with 10 degrees of freedom, there's still some unmodeled autocorrelation, it looks like, but that's what is actually happening here. But this test would be telling you that you needed to increase k. So you would go back and you'd double k if you follow the thing, and then you'd look at your summary, and okay, it hasn't made any difference, right? But this would still keep telling you that you needed to increase k. And it's all because this heuristic test also doesn't know that the data are autocorrelated. Now, in some situations, it would start using more degrees of freedom. It would keep eating up all these degrees of freedom. It hasn't really changed here in this fit, but it could keep making a more complicated fit. And then k.check would keep telling you that it still wasn't satisfied, right? And that's the problem that we sometimes got into with modeling time series. All right, just set that back. If we now do that with neighborhood cross-validation, it'll still tell us that we have a problem, but we can ignore k.check really here, okay? And I'm just going to look at the different smooth fits now using my function here. So let's see, what has it actually done for the Hadley Center data, okay? Now, these data don't have a huge amount of autocorrelation, but in the blue is the fit if we assume the observations are independent, which is a bit of a stretch for time series data. And in orange, hopefully you can see in orange, we have the fit that's due to the neighborhood cross-validation. And they look very similar. It's just that the neighborhood cross-validation is that little bit smoother. It's not showing quite so much oscillation, especially earlier on in the record. Okay. But I didn't have to tell it what the order of the correlation was. All I had to do was say I wanted, in this case, to leave out 5 observations before and 5 observations after each of my observations in the time series. And if you look at Dave's blog post, he has a couple of extra examples of different structures that you can use for doing this neighborhood cross-validation. Okay, one of the questions that's in the chat is, why did I do some like this? why didn't I do S of chick with RE for a random effect? So I've got one here. I guess I didn't explain this. This one here is just saying that the chicks have a random intercept. This first chick was going to maybe is a bigger one. This one, the next chick is a smaller one. So they just have some some are bigger, some are smaller than, but they all follow the trend for their diet. Whereas with this factor smooth one, now I'm saying instead of the just having a different intercept for each chick, I'm saying each chick can have its own growth curve. And that's the difference. Sorry, I skipped over that when I explained that particular model step. Okay. Right, well, I'm a little bit running out of time, so I will go a little bit through the where do I want to be? I want to be in meld. I'll go through some of the extra bits in gratia now, but I won't dwell on too much, and maybe I'll arrange another live stream when I've actually figured out how my technical issues. Okay. So I'll go over, I won't go over this in a lot of detail in gratia. I'll probably do another live stream. Okay. So what's new in gratia, which is my package for working with GAMs? Well, there's a whole lot of new functionality. And if you go and look at the web page on GitHub or follow up from CRAN, you can see the changelog. We've already seen the conditional values function. So as you start to build these models, these hierarchical models, or more complicated models, it becomes harder and harder and harder to actually understand what the model is encoding, especially when effects of the same covariate, like diet, for example, or the effect of time is spread over multiple terms. So conditional values just is a quick way of allowing you to say, okay, I want to look at these combinations. What does my model say in those combinations? So it's quite useful. It's quite user-friendly. It's modeled after the plot predictions function. It doesn't have as much functionality as that function does from marginal effects, but it's simpler to use, and and hopefully it'll be useful for people. I end up using it a lot now. One thing I will talk a little bit more about, though. Okay. So model diagnostics are hard, especially when you've got non-identity link functions and you've got discrete responses. They are hard in GAMs as well. And the problem is that in many of these things, and with discrete responses, we would actually expect to see patterns in our deviance residuals. So quantile and pit residuals can help, and I'll just explain a little bit about these. But here we've got some data. It's simulated data, and I'm going to simulate data according to a negative binomial. So it has some form here that Eric actually created. And then here I'm saying that my observations are negative binomial. So they're draws from the negative binomial distribution with mean given by, well, this is the log mean, I guess, here. Right? So I'm going to fit the wrong model. So I'm going to fit a GAM with a Poisson family of Poisson distributions. So I'm going to assume they're Poisson, and then I'm going to fit the right model where I'm fitting it with a negative binomial here. And I can look at my residuals, and if I do that for the wrong model, we see that things are wrong because there's a clear increase in the variance. But we have these lines here, which are all, there's the zeros, the ones, the twos, and so on in the data. Now, this is the correct model, but we also have these lines in here, all right? And that's just by virtue of the fact that the data are discrete. And there's not an awful lot we can do about that. And so it gets hard sometimes to explain to people or to understand which features should we expect to see and which ones are clearly problems, right? Now, it's not always going to be as clear as this. There's a clear big problem in the Poisson model that you can ignore all these lines over here, focus on fixing this. The logical step would be to go from the Poisson to a negative binomial, and If you do that, then things look a bit better. But people often, especially when they're starting out modeling, they worry about what these lines are. They think those lines shouldn't be there. Coming from a linear modeling kind of framework, you're taught that these shouldn't be there. They should be randomly scattered. Okay. So the first type of that are interesting here are pit residuals. So those probability integral transform residuals, they are plugged through the cumulative distribution function for the family that you've used to fit your model. And they essentially turn the residuals into something that should be uniform, have a uniform distribution. The quantile residuals then do an extra step. They take those uniform pit residuals and they shove them through the inverse cumulative distribution function of the Gaussian distribution, and therefore they should look approximately Gaussian if you've got the right model. So pit residuals should look approximately uniform if the model is correct, and the quantile residuals should look approximately Gaussian if the model is correct. So if I look here, this is my pit residual for the Poisson on the left. These are the pit residuals. They should be essentially uniform. And you'll see that it's actually quite hard to see in this particular set, but you'll notice that there are big gaps here. And that's because you've got much more density out at the edges, and that's illustrating this non-constant variance. That's actually easier to see if you look at the quantile residuals, because now you don't have those bands, okay? You don't have the bands in that we saw in here, okay? But we do see the non-constant variance problem, okay? So these pit residuals and quantile residuals are quite useful as diagnostics for your models. They're a similar idea to what Dharma does. Okay, they're generated in a slightly different way, but they're essentially trying to do the same sort of idea as Dharma. Dharma keeps them as sort of uniform and also uniform on the linear predictor. I don't do that here, but you know. For the correct model, these are the pit residuals for the correct model. They do look more like a random scatter over it. And if we look at the quantile residuals, which should have an approximate Gaussian distribution if the model is correct, then these things look more like what you would expect to see if this was a linear model. Okay, so this is using the residuals versus linear predictor function in Gratia. They're available there. You can also do this with the histogram versions of the plots. These are supposed to be uniform if the model is correct. They don't really look particularly uniform for the negative binomial, even though that's the correct model. But this is a relatively small data set, so we should expect some variation here. If there was more data, they would look more uniform. The quantile residuals do kind of look like we would expect. This looks like a Gaussian sort of distribution. This one doesn't. This has got fatter tails. Okay, so it doesn't look like a Gaussian. I guess I should superimpose a Gaussian distribution to these, so just to help. Okay. Now, at the moment, these things, just like Dharma, they don't work for all of the families in MGCV. And that's because the families, as you saw, there's like 30 different families. Not all of them have the necessary cumulative distribution and quantile functions. Inverse of the CDF, I guess. I'm not sure which way around they are. But we're adding more of these. So my Gratia package is adding some, mgcv is adding them, but ultimately our aim, so this is mgcv is Matteo Faciolo's package for working with GAMs, doing plotting and lots of other fun stuff. And we aren't going to keep them in our own packages. We are going to get them into mgcv utils, so we're not duplicating effort. All right. But while we're working on this, we've got functionality in Gratia to use them, and mgcvs. They work slightly differently, but we have the functionality there. And ultimately, we're going to get them into Dave's mgcv utils package, hopefully. Okay. As far as Gratia is concerned, they work for the standard GLM families, but not yet. I haven't got it quite working for inverse Gaussian. But we also have negative binomial and Tweedy families working fine here as well. Okay. I was, I guess, forecasting that I would run out of time. I'm just going to go to Gratia's webpage and just check that there are no questions in that were posted in the discussions. I haven't noticed anything. Let me just check. Nope. So apologies for the technical problems, but I think we will leave it there. What I will do is I will do another live stream maybe a little bit later in the year where I talk a little bit more about new things in Gratia. One of the things that I'm actually really quite pleased with is the posterior sampling functionality that we've got, because this allows you to do simulation-based inference, and it allows you to do things inference using your model that you wouldn't have thought possible. And it's essentially a bit like, well, these GAMs are Bayesian, but we're using we're without doing Markov chain Monte Carlo to fit the model, but we can simulate from the posterior distribution in a similar way as we do when we're doing a Bayesian fit, and we can use that to do inference. And so it's quite a nice way of doing inference with these things. But that, I'll have to leave it there. I'll hang on for a minute just to see if anybody has any additional questions. If you do, you can pop them into the live chat. But otherwise, if I don't see any questions popping up, then we will call it an evening. And thanks for bearing with me while we had the technical difficulties earlier on. It was my fault. It was actually, I didn't realize something and I thought I'd started the wrong stream and I hadn't. I just ended the one you were all waiting to watch. So yeah, I will work on my YouTube streaming stuff, skills for next time. So I will, I'll just wait and let the stream catch up. If you do, as I said, if you do have any questions, you can pop them into the live chat. Okay, so yeah, there's a question here. So when using SZ, do you have to worry about the ordered versus the unordered factored issues? No, and I actually haven't look to see if SZ does anything different. I mean, it's not meant to do anything different with, it's not meant to do anything different with the an ordered factor. So I think it will just treat it as a factor and work. But yeah, you don't have to do anything. You don't have to code it as an ordered factor and then fiddle with the contrast to get it looking like a normal one and all the rest of it that you have to do. You can just use an ordinary factor like you would with the bi-variable. Okay. So that's, yeah, it's actually really simple to use. And as I said, if you're doing anything where you've got kind of experimental treatments and then subjects within those treatments or things like that, then it is actually a very useful basis to have. The one downside, well, or two downsides, is that it only allows you to have a smooth of a single variable, and that's frustrating because it would be nice if you could have tensor products, but the way they are created, they're already a tensor product under the hood just to get these univariate smooths. So I'm not sure if it's how easy it is to turn them into like having two-dimensional smooths, but interacting with the factor. And the other thing that's a little bit more complicated, and I was trying to rack my brains as to why, what the setting was, but I think what's going to happen, what might happen is that if you have two continuous variables that you're doing this for, then you can end up having, there was a situation that I was getting into where I wanted to have the main effect in there once, right? But by using the SZ smooth, I had to have the main effect in there multiple times. And it was in a much more complicated model. And I can't quite remember exactly why this was there, but there is this. If you start to get into a more complicated setting with the SZ smooths for lots of different factors and lots of different covariates, you can end up having the main effect part potentially in there a few different times. Or, oh no, absolutely, it wasn't that. It was the means. That's it. It's the group means. That's the bit. Okay. So let me go back in here. When you're doing SZ, you'll notice that there's no parametric term, right? So this term here, the SZ one includes the group means. So if I now wanted, so the group means of F. So if I wanted to have S of Z by F, so I wanted to do this plus S of Z, so the equivalent, but for S of Z as well. So I had a smooth of X and a smooth of Z, and then a constrained factor smooth of X and F, and a constrained factor smooth of Z and F, right? So I've got these two different continuous variables. The group means would get included in the model twice, and that isn't identifiable. So the problem is when you have models that are where you want to have a continuous variable interacting, where you've got two continuous variables and you want them to interact with the same factor. That's where you get the problem coming up. And I emailed Simon about it, but I didn't hear sort of back anything about it. You know, Simon's busy. He puts these things on his to-do list, and if you know, sometimes you get an answer really quickly because he's already thought about it. Sometimes these things hang around for a while and may or may not get added. So, okay. Well, thanks for the comments in the live chat. Again, apologies for the snafu at the beginning. I need to work on my streaming skills. But anyway, thanks a lot for your attention. I will leave things there. And if you do have any questions, you can follow up in the discussions for Gratia if you want. You can find me on social media and ask me questions there. But anyway, thanks a lot for your attention, and I will see you in the next live stream. Okay, thanks a lot. Bye-bye.